In this lecture, let's talk about reaction quotients. In earlier lectures, we talked about chemical equilibrium and we introduced the equilibrium constant. In this lecture, let's talk about what happens when we have initial concentrations and we don't know if the system is at equilibrium. If the system is not at equilibrium, which way will it shift in order to reach the equilibrium constant? So we'll set up what's called the reaction quotient. We'll call it Q, and it's set up using the law of mass action. So essentially the same way that we set up the equilibrium constant or the equilibrium constant expression. And the reaction quotient is the concentration of the products. In this case, NO is raised to the 2 because of the coefficient of 2. And this will be divided by the concentrations of our products raised to the power of these coefficients. Now here, each coefficient is just 1. So this is just the concentration of N2 times the concentration of O2. So we'll go ahead and insert our concentrations. And when we plug this into the calculator, we'll get this ratio. The number that I get here is 8.33 times 10 raised to the minus 4. And now we can compare here. You can definitely tell that our reaction quotient is smaller than our equilibrium constant. So Q is less than K. So this ratio is too small. The system is not at equilibrium. Because it's too small, it needs to get bigger. So look at the math. How does this ratio increase? We need more product and less reactant. So when Q is less than K, the system will shift to the right. We can also say the system will shift to the products side. Let's do another example. So in this example, we have the reaction of PCl3 reacting with chlorine gas to yield PCl5. Here I'm giving you the Kp, so this is the equilibrium expression with respect to the partial pressures, and the Kp is 3.8 at 450 K. I'm giving you the initial partial pressures, and let's determine our reaction quotient. So Q is equal to the partial pressure of PCl5, and that's raised to the 1 because of the coefficient of 1, divided by the reactants. So the partial pressure of PCl3 times the partial pressure of Cl2, both of these are raised to the 1 because of the coefficients in the balanced equation. And we'll go ahead and plug in our initial partial pressures. 1.2 over 0.25 times the partial pressure of chlorine, 0.50. And when we calculate this, we get a value of 9.6. Interesting here, compared to our last example, Q is greater than K. So this number is too large. This system needs to shift so that this ratio goes to 3.8. This ratio needs to get smaller. And if you look at the math, in order for the ratio to get smaller, we need less products and more reactants. So when Q is greater than K or Kp, there's a shift to the left. You can also say there's a shift to the reactant side. Let's close with one more example. So So here we have the reaction of NOBr, 2 moles, to yield 2 moles of NO and 1 mole of Br2. At 298 K, here's our equilibrium constant. So again, let's set up our reaction quotient. Here are the initial concentrations. The law of mass action says that the reaction quotient is the concentration of NO raised to the 2 times the concentration of Br2 over the reactants. The concentration of NOBr raised to the 2 because of that 2 coefficient. So let's plug in our values. And when we plug in our values, we will get a reaction quotient of 1.8 times 10 to the minus 3. So again, like our last example, 10 to the minus 3 is larger than 10 to the minus 4. Q is greater than K. So again, let's look at the math here. This ratio, using the initial concentrations, is too big compared to our equilibrium constant. This ratio needs to get smaller. So if you look at the math, this ratio gets smaller when there's less products and more reactants. So here's another shift to the left. You can also say there's a shift to the reactants side.